Hi everyone. Today we're continuing our discussion on gases, and in particular we're going to discuss our first gas law, which is called Boyle's law, and this law relates pressure and volume. So this law is just named after a scientist who did work on figuring out the relationship between pressure and volume. But you don't have to remember the name of the law, just the relationship. So in this law, there is an inverse relationship between pressure and volume. So pressure is proportional to 1 over V. Or we can say that pressure is inversely proportional to V, volume. So what this means is when volume increases, pressure decreases. Now, this only works if temperature and the amount of the gas in moles remains constant. So we're not changing the temperature of the gas, we're not changing the amount of the gas, we're only changing pressure and volume. And when we do that, we find that as pressure increases, volume decreases. And as volume increases, pressure decreases. So it's an inverse relationship. All right, so let's look at a figure kind of showing this same idea. So in the figure to the right, we have a gas in a cylinder, and it looks like we have 6 moles of gas there, or 6 gas particles, I should say. Now, on the top of this container, we have a movable piston, so that piston can change depending on the pressure of the gas. So let's say initially the pressure inside of this container is 1 atmosphere, and the volume is 4 liters. Now, if the volume decreases, so let's say we push that piston down, so we've reduced the volume of the gas to 2 liters, so we've decreased it by half. The pressure inside the container is going to increase to 2 atmospheres. Okay, so the volume decreased by half, the pressure increased by a factor of 2. And that kind of makes sense when you think about what pressure is. We said previously that pressure is a force, and that force is exerted by the gas particles and their collisions with the container or the walls of the container. So if initially we have a lot of room for the gas to move around in, they're not going to hit the wall that often. Whereas if we decrease the amount of room that the gas has to move around, they're going to collide with the walls more often. So maybe, for instance, this gas particle here hits that, then that, that. Maybe it's just kind of moving around like that. Now, the same particle, if it's in this smaller container, is going to consistently be hitting the walls. Now, again, we're not changing the temperature or the amount of the gas. That's both, or those are variables that are staying the same. Now, what's also interesting here is if we multiply the pressure and volume for the initial condition, we get 4 liters times atmospheres. If we do the same thing with our second condition there, we have 2 times 2, which is also 4 liters times atmospheres. So what this tells us is that the product of pressure times volume is constant when temperature and amount of gas is held constant. So now we can write a law or an equation where P1V1 equals P2V2. Now this is kind of similar to our dilution equation, right? C1V1 equals C2V2. So, except here we're thinking about pressure instead of concentration. Okay. So again, pressure times volume is a constant, provided that the temperature and the amount of the gas remain the same. So for instance, let's say we have an initial set of conditions where P1 is equal to 8 atmospheres and V1 is equal to 2 liters. If we multiply those two together, we get 16. Now, let's say that we increase the volume by a factor of 2. So now we have 4 liters of volume. The pressure is going to decrease by half. So we'll have a pressure of 4 atmospheres. Now 4 times 4 is also 16. And then let's say we multiply the pressure or the volume by 2 again. So now we have 8 liters. The pressure is going to decrease by half again to 2 atmospheres. Now if we multiply those two together, again we get 16. And that's what gives us Boyle's law, that fact that pressure times volume is a constant for a particular system. Now, we can also think about this in terms of our bodies. So let's kind of relate this to our lungs and breathing. So during inhalation, our lungs expand, and that means the volume of our lungs is increasing. Now, as the volume in our lungs increases, the pressure decreases. And air is going to flow toward the lower pressure, which is in our lungs. So when we breathe in, we expand the lungs, and air is going to naturally flow in to fill that space. Now, as we exhale, our lung volume decreases. So now there's not as much space. So the pressure within our lungs increases. And air again is going to naturally flow towards an area of lower pressure, so it's going to flow out. So whenever you're breathing, you can kind of think about pressure and volume, although don't stress too much about breathing. All right, so now let's apply Boyle's law to a problem. Let's say that we have a sample of Freon gas. Now, Freon has a chemical formula CCl2F2. So we have a carbon that's bonded to 2 chlorines and 2 fluorines. And don't forget your valence electrons. So it looks something like that. And this is something that was used in refrigeration systems a long time ago, but it was found that Freon was negatively impacting the ozone layer. So eventually Freon was discontinued in refrigeration systems. I believe that it was also used in some air conditioning units, so that has also been discontinued as well. All right, so what is the new volume of an 8-liter sample of Freon gas initially at 550 millimeters of mercury after its pressure is changed to 2,200 millimeters of mercury at constant temperature and moles? Okay, so let's write out what we know, what we're given. So we're told that initially we have an 8-liter sample of Freon gas. So that will be our initial volume. And then the initial pressure, P1, is 550 millimeters of mercury. And then we're going to change the pressure to P2, which is equal to 2,200 millimeters of mercury. And then the only thing we don't know is the new volume, V2. Okay, so now we're going to use Boyle's law, which again is P1V1 equals P2V2. And we're just going to plug in this information we've been given. So we'll multiply 550 millimeters of mercury times V1, which is 8 liters. And we'll set that equal to our new pressure times our unknown variable V2. Okay, so then we're going to make sure we isolate V2. So we're going to need to divide both sides by 2,200 millimeters of mercury. Okay, so now let's check that our units all cancel. So this cancels on the right, our 2,200 millimeters of mercury. And then that same unit cancels on the left. So now we're just going to multiply 550 by 8 and divide by 2,200, and our final unit will be liters. All right, so let me pull out my calculator. 550 times 8 divided by 2,200. Okay, so I get a value of 2.0 liters. Now let's do a quick sig fig check. So how many sig figs does 8.0 have? 2. What about 550? Only 2. So we don't see a decimal point at the end of that value, so that 0 is not significant. So only the 5 and the other 5 are significant. What about 2,200? How many sig figs does that have? Also 2. Again, there's no decimal point at the end of the number, so those 2 zeros are just placeholder values, and they don't count as significant. So our final answer should also have 2 sig figs since we're multiplying and dividing. All right. And here are the solution slides if you need those later. So let's do another problem. A sample of oxygen gas has a volume of 12 liters at 600 millimeters of mercury. What is the new pressure when the volume changes to 36 liters at a constant temperature and amount of gas? So remember, lowercase n stands for amount of gas. Okay, and then we have some multiple choice options here. So if you want to try this problem on your own first, feel free to pause the video, and then when you unpause, we'll go over it together. Okay. So again, I'm going to write out what we're given. So it looks like we have our initial volume and pressure. So V1 is equal to 12 liters. P1 is equal to 600 decimal millimeters of mercury. So that decimal is going to tell us how many sig figs we have. And then we're trying to figure out what the new pressure is when the volume changes to 36 liters. Okay, so that tells us we don't know what the new pressure is, but V2, our new volume, is 36 liters. Okay, so again, we're using Boyle's law. And we're just going to plug in all the values we have here. So we have 600 millimeters of mercury. Oh, I forgot my decimal. Times 12.0 liters. And then that's equal to P2, which we don't know, times V2, which is 36.0 liters. Okay, so now we're going to isolate our unknown variable. So we're going to divide both sides by 36 liters. And let's make sure our units cancel. Let's see, liters cancels. Okay, so we're left with a unit of pressure, which is exactly what we want. All right, so now we just have to plug into our calculators. Let me pull mine up. Let's see, 600 times 12 divided by 36. Okay. So my calculator gives me a value of 200 millimeters mercury. But let's look at sig figs. All right, so how many sig figs does 12.0 have? 3. So that 0 at the end is after a decimal point and after a non-zero digit, so it is significant. Now what about 600 with a decimal at the end? How many sig figs does that have? Also 3. So that decimal point tells us that those two zeros are significant. And then what about 36.0? How many sig figs does that have? Also 3. All right, so that tells us our final answer should also have 3 sig figs. So I'm going to put a decimal at the end of my number to make sure that I indicate there are 3 significant figures here, not just 1. All right, so now let's go to our next problem, and this will be our last problem for this law. This one is more of a visual problem. So let's say a sample of helium gas in a balloon has a volume of 6.4 liters at a pressure of 0.7 atmospheres. Now at 1.4 atmospheres is the new volume represented by A, B, or C. Okay, so we've got our initial balloon here with the initial volume of 6.4 liters, and the pressure is 0.7 atmospheres. Now, it looks like we're doubling the pressure. So remember, pressure is inversely proportional to volume. So take a guess. Do you think that the new volume is going to stay the same, which would be B? Is the new volume going to be smaller, which is A? Or is the new volume going to be bigger, which is C? So I'll let you think about it for a minute and then we'll go over it together. Okay, so remember, pressure is inversely proportional to volume. So we're increasing the pressure, which means we're going to see a decrease in volume. So that means A is the correct answer. We're going to have a smaller volume. Okay, now you could have done process of elimination. So you could have said, well, I know that the volume is not going to stay the same because pressure is changing. So we could have eliminated B right away. And then we just had to figure out, with an increase in pressure, will we have an increase in volume, C, or a decrease in volume, A? And since we know that they're inversely proportional, we could say the volume is going to get smaller. All right. So next time, we're going to talk about another law called Charles's law. And this law relates temperature and volume. So I will see you then.